And if you're suited for PhD, exactly the same things will happen. You will still be frustrated when your calculations don't work out, and you will be
Yeah.
sad when your ideas fail.
So were you influenced by Lee Smolin?
I was influenced by Lee Smalling. So
Okay, that
Computer
makes
Physics
sense.
came out in 2006, and I started my
Right.
PhD in 2009.
Welcome to this episode of Phymaths podcast. Today, our guest is Dr. Nirmalya Kajuri. He is a faculty member at IIT Mandi. He did his PhD from Institute of Mathematical Sciences at Chennai, and he did his postdocs from IIT Madras, Chennai Mathematical Institute, and Indian Association for the Cultivation of Science, or IISERs, Kolkata. And he works on quantum gravity, holography, and cosmology. So, first of all, welcome to the podcast. I want to start this particular episode from your PhD, because
Okay.
I think you have a very interesting journey, because you started with loop quantum gravity, and
That's
then
right.
you and then you transitioned yourself into string theory. I think I've not seen any other person doing that. Well, there might be people who did that, but I've not seen any other person doing that. So how was that transition? And what made you to do that transition?
Well, okay. That's an interesting question, Hassan.
Yeah.
Uh, so, so initially, I came into quantum gravity. I got interested in quantum gravity from when I was roughly an undergrad, when I was studying special relativity first. And I figured that I did not really understand what space-time was, in the sense that from an operational perspective, what is space and what is time? So those were the questions that I got interested in. Like, okay, uh, what really is time? Because we don't see time, we see matter, and we count matter. We count we when we have to calculate space. When we say what is the distance between the two things, we use rulers, and we measure space time using rulers. So what we have are rulers, and what we have are clocks, but we don't actually see space time directly. So is there really something called space time? So those kind of Machian point of views got me interested in what is space time. And from then on, I thought, to really get to the bottom of this, I have to learn quantum gravity. And because I was coming from that kind of perspective, where I wanted to understand things like what space-time really meant and so on, it felt like string theory was not like seemed to be answering those questions. So string theory, I felt that did not answer all my questions, in the sense that the people who were working on string theory seemed to be doing something. My understanding at that time, which was flawed, was that it's a background dependent approach, and where people study strings on a given background. So space and time are fixed, whereas the background is space and time are fixed, and you're studying something perturbatively on it. Whereas people in loop quantum gravity seem to be more interested in the kind of questions I had in mind, is like, what is space and time really? So they were trying to quantize non-perturbatively space and time itself. And so that kind of thing, and the communication that was put out there by loop quantum gravity people, seemed to be more in tune with the kind of more philosophical questions that I was thinking of. And so I thought this would be a good starting point for me to understand quantum gravity, particularly because also when you want to quantize something, you probably want to check that whether directly quantizing that thing works or not before trying other approaches. So in that sense, canonical loop quantum gravity was an old school approach, where you just directly try to quantize the gravitational field. And then you want to see, like, why does that not work? So that would be a good point to start learning about quantum gravity. And so I went into loop quantum gravity. Although I did not exactly work on loop quantum gravity, I worked on something called polymer quantization, which is where you kind of use the techniques of loop quantum gravity to work on scalar fields, to kind of as a test for those techniques. So yeah, so that's how I got into loop quantum gravity.
One thing that I actually wanted to ask you is that you did your PhD in this thing called polymer quantization. By the way, I think I read somewhere that there were some people who actually tried to, give you a paper to review that was actually on polymers. They thought that
That's
you
right.
actually work on polymers, right?
I got
And that
several papers like that and several requests from journals on polymer science
right.
to write.
And that actually reminded me of this incident that I had. So I used to use this app, but I don't use that app anymore. That app is called Researcher, and what it did is that if you did if you gave it some keywords, then what it could do is that it could bring all the papers from the journals that you select and give you the your daily feed of papers for those keywords. And I remember that I used to have this word swampland, and
Mhm.
some of the papers that it was giving me was from forest science. And I was like, that's interesting, right? So this polymer thing actually reminded me of that thing, that okay, if you just use keywords, then this can happen.
Yeah.
My main question is that how did you try? Oh, and okay, before that question, um,
Mhm.
it's a guess. I mean, let me know if it is correct or not, because one thing that you said is that you thought that string theory is a background dependent theory.
Mhm.
So were you influenced by Lee Smolin?
I was influenced by Lee Smolin. So
Okay, that
Computer
makes
Physics
sense.
came out in 2006, and I started my
Right.
PhD in 2009. So,
Okay.
so I read it
It
before,
makes
and
sense. It
it was
makes
one of
sense.
the, yeah, for sure.
So, then my next question should be that how did you make, was this transition difficult for you? Because then you have to learn this whole new field called string theory, and
Mhm.
and I think the more important question here is that what made you to do that transition? How did you understand that okay, string theory is the thing that you actually should do, and it's not loop quantum gravity that you should do?
Yeah.
So what
So
made you realize that?
as I worked in loop quantum gravity, slowly I kind of, there were two things. One was the problems in loop quantum gravity that were open problems that I thought were important problems to be solved. Those were of a very mathematical nature. I'm talking about canonical quantum gravity, which I thought was more rigorous. And I'm not that kind of a mathematical person. So I thought this was not suitable for me as such. So this did not seem to be a field where, that needed me, or where I could make a interesting contribution, or where I would enjoy working so much, because I'm not a mathematical kind of thinker. And secondly, I thought that, and of course, those problems were very difficult problems. And I also felt that the difference between string theory and loop quantum gravity was that in string theory, you are getting a lot more than you actually put in. So one of the things where if something is more promising than the other, in science, you develop this kind of intuition that when you have a field where you are getting more than you're putting in, more than your assumptions, it's giving you a lot of rich structure out of it, then that seems to be correct. And especially when that is connecting with physics that you know. So there was a particular transition point for me, which is when I saw the Ryu Takanagi conjecture in a talk. So this was, so at that point, the Ryu Takanagi conjecture was maybe 6 years old. I didn't know of it, but I was attending a talk, and then someone showed that, okay, so there is this thing where you have a duality, ADS-CFT duality. There's a bulk one side, boundary theory on the other side. And what you can do is you can calculate the entanglement entropy in one theory, and from the area of a surface in another theory. And what was particularly striking was there are these kind of inequalities, there are these kind of constraints that entanglement entropy satisfies. And some of them are very complicated to prove. There are like pages of proof from the 80s. And those could be gotten in like 3 lines from the ADS side, just by some geometric computation. So that was to me like magic. And I thought that when this is happening, surely there is something to it, something more to it than, this is not something that was put in by hand in the theory. This is coming out on its own, and it's almost like a miracle that's happening. And so that convinced me that, this is where I should look, because there is something true about this. There's something rich about this. There's something mysterious about this, which is not something I was getting out of loop quantum gravity, where almost everything that we were getting out of it was put in by hand. So there was very little I felt that was, surprising coming from that theory. So
I see.
this was one of the kind of transition points for me, that, okay, this is where I have to go. And then
Right.
also other things, because string theory was also connecting with the field theory, things that we know in non-trivial ways. So then I
Well,
decided,
so let me play the devil's advocate for a minute.
sure.
So somebody may say that, well, but why do you care about, ADS? Our universe is not ADS.
Yeah, so that's a valid question. That's a good question. But I would answer that because how is the universe different from ADS? The differences mainly manifest when we're looking at large distances. So at large distances, because as we go, far away, our universe is expanding, whereas the ADS universe is kind of like a box. So it's a boxed-in universe, and that difference manifests when you kind of go look at large distances compared to the ADS radius. When you are looking at smaller distances, the differences are less. So it's a much less difference when we are looking at very small UV scale considerations. So for me, the intuition was that if I'm looking at those questions, then the answers should not be too different. If I'm looking at scales much smaller than ADS radius, then the difference would not be too much. So one should be able to take at least some of the intuition of what is happening here and be able to transfer it to our universe. For example, if I'm looking at something like a black hole information loss paradox, a black hole evaporating in ADS, the resolution of black hole information loss paradox, whatever it is in ADS, I would not think that it would be too different in our space-time, because it's not something that depends on your ADS radius, at least for evaporating black holes.
I see. Yeah, please continue.
Yeah. So that is my answer.
So, in short, you're saying that Ryo-Takayanagi conjecture was one of the things that made you transition from loop quantum gravity to string theory.
Absolutely.
Okay, so before we continue, I think there are some aspects of your PhD, I think, that you have talked about online. I think that those aspects can be very helpful for students who are doing PhD right now, including myself, by the way. So you said, I mean, you can tell the story in your own words, but if I summarize, what happened is that you had two papers, and when you were when you wrote your thesis, you discovered that you actually generalized the results by one of the prominent physicists in your field. And what happened is that that prominent physicist made a mistake because I think they did not include some terms that it should have included.
Right.
And that was actually a very panicking situation for yourself, because you had written your thesis, right? So I think I have two questions here. One question is that how do you keep yourself composed in such a situation, because it's a very panicking situation? And the second question is that, does it give you this lesson that you should not assume that just because some physicist is a big name, then therefore that person cannot make a mistake?
Yeah. To answer the second question first, absolutely. You cannot ever assume that, and you have to check everything. So that was the painful lesson that I learned, because I was at a point where it felt like the PhD is going to slip out of my fingers, you know. And and that was solely because I had not checked the calculation. So my advisor. So what happened was, to recap the story, my advisor. So there was this paper that I had written on generalizing a result by a prominent physicist, and there was one step that was kind of a little bit icky, and my advisor had told me that you should check it. It does not seem to compute, so you should really check that step, how it's working out, how some terms are canceling. I did not do this. I thought, okay, this is the prominent physicist, this must be right. And in my mind it seemed to work, like this cancels with that, it should work. And also he has done it, so it's fine. But it was not fine, which we discovered when I was writing my thesis. And I thought, okay, let me once and for all, do this computation. When I tried doing it, it was not working out. So then I was really panicking. I took it to my advisor, and we sat down and we tried for a long time. Nothing worked. So indeed, I can't say that I kept myself composed. At least I don't remember being so composed. I was just like, panicking. I didn't know what was going to happen. But then I sat down in the evening, and what happens is, when you have a problem in hand, it kind of composes you in some sense, because you want to solve the problem. So you try different things. And then I had an idea that, we are doing it in the position space, or something like that. We could try doing it in the dual space, and that worked. That kind of resolved the problem. The terms canceled, and we got an answer at the expense of some extra summations, where it gave a fine find closed form result. So yeah, that happened. That was a very but again, it's such a good story that I don't fully regret making that mistake, but lesson learned.
Right. But I think to get this idea that you have to do this calculation in the dual space, don't you need a composed mind? Because at least I can't, imagine getting that idea with a panicking mind. I mean, I will just panic. I don't get this idea.
Yeah, as I was saying that I was like, because there was this problem at hand that kind of composes you because you want to solve the problem. This on the one hand you're panicking, but also as a lot of us are problem solvers, you also want to get down and solve the problem.
Right,
So that
right, right.
problem kind of composed me, I would say.
There's another thing. I think about that you have talked about in some podcast. I think, and that's actually a very good point because I think this is something that uh, you know uh, young researchers should learn about. So there is this tendency in a lot of people who think that before you do research, you need to know everything.
Mhm,
And the thing is that I think you said somewhere in some podcast that you also had this tendency, I think. But then
mhm,
you have to learn that you don't need to know everything before you do your research. And that actually reminds me, of the fact that even Steven Weinberg used to think that
mhm,
he needs to know everything. And he actually wrote this, I think. I can't remember the essay where he wrote this, but there's some essay where he wrote that he thought that I don't know anything, I cannot do research, right? So, do you want to talk about that? There is that how to overcome this tendency, because I understand that this is a natural tendency. I felt that, and I know that a lot of young researchers feel that they need to know a lot of things, or well, sometimes they think that they need to know a lot of things, but sometimes they think that they need to know everything that is known about this thing before you can do some new work in this field. So, what do you say about that?
yeah, I didn't exactly have that kind of tendency. What my issue was more that I didn't think that I should ask for help. I felt that
Oh, okay.
I should do things on my own. I should be able to learn everything on my own. That it was expected of me that I should be able to read all papers on my own. And even if I got stuck, did not go for help to my advisor,
Right.
which is something I should have done. The other thing that you're talking about is kind of, you know, you feel like you have to know everything before you start research. That is something I never had, because my problem was opposite. I would jump at problems even without knowing the background. So I was like completely opposite that way. So
I
my
see.
issue was I would start some problem and then I realized that I don't have adequate background to do it.
I mean, for example, when I was learning, supersymmetric sigma models for the first time, there you have, this scalar potential. And, I learned that, okay, the scalar potential can be seen as, the scalar potential can be seen as something such that if you take two derivatives of this thing, you get the scalar matrix. And then I told myself that, okay, now I need to know everything about Kähler manifolds before I continue. And I'm sure you know about Kyriakos Papadodimos, right?
Right.
Right. So he was at ICDP, and I actually talked to him about this thing, and he said to me that, well, he had the same tendency because he thought that if there is a new math word that appears somewhere in a paper that he's reading, then he used to tell himself that, now I need to know all of this mathematical theory before I, I can read this paper, and I could relate to him. But then he told me that again, this is something that you have to, suppress because this is not how researchers work. Um, so I was actually talking about this thing,
Right.
and
I had that problem with math. With math, I had that
right.
problem because I did not have the mathematical background. And when I would see something mathematical like that, then
Hmm,
exactly the same thing. I thought, I have to learn all of math to that point to kind of get there, and that
I
was a
see.
problem. You kind of realize that you can't do that. That research is a very non-linear field. That you have to get rid of your linear mindset. That you cannot learn things linearly, that you cannot build up to it and then this and then this. That's not how it works.
Right.
It's non-linear. You know a little bit here, there, and even that could be enough. But it comes
Yeah.
with experience. Once you get experience, you realize that the thing that you needed may not be that much. You might need like maybe a little bit background, maybe one theorem for all of your work. In theoretical field,
Right.
it often works that way. But then there's
Exactly.
a lot of, like ecosystem that you get lost in.
Right. For example, I remember this story that I think in 2021 probably uh, I was actually reading a paper about some application of F theory. Now in F
Mhm.
theory, you need a lot of algebraic geometry. So what I
Mhm.
started to do is that I left that paper and I started to study algebraic geometry on its own. And well, so algebraic geometry can be done for any field, but in string theory, you don't need any other fields, other than complex numbers. So you just need complex algebraic geometry. So I just started to learn algebraic geometry on its own. And then my advisor said that if you do that, then I think your PhD will need probably 10 years. Don't
Yeah.
do that. And then he told me this joke, and that I will never forget. Told me that there's this joke that physicists tell each other about this kind of stuff. He said that if there's a physicist and there's a mathematician who are actually climbing a cliff, so the physicist goes to the top of the cliff, and then he sees another cliff and he wants to go to that to the top of that cliff. So what he will do is that he will make a bridge to the top of that cliff. So the mathematician comes to this cliff now, the first cliff, and he also wants to go to that particular cliff. So what he tries to do is that he will try to dig up the dirt and fill the valley between the two cliffs. So don't try to do what the mathematicians do. Try to do what the physicists do, right? So that was actually a very good lesson for me, at least. But about this asking for help thing, um,
Mhm.
there are a lot of people actually who I know who actually have the same problem, that they think that um, asking for help maybe portrays a bad picture of you in the mind of the advisor. So can you relate to that or no?
Yeah, not exactly. I mean, I just thought that I have to do this. It's just something that a PhD student is expected to do. Not so much that the advisor will judge me, but that it's a kind of a failure in some way. That it's
I see.
that if I'm you expect that, okay, if I know this much, then I should be able to do this, in that kind of sense. That if I've learned so far, then I should be able to do this. If I'm not doing this, then maybe I'm not fit for I'm not smart enough to do a
Right,
PhD. So in that kind
right,
of
right.
way, I felt that
I
I
see.
should be able to do this,
I see.
which
Uh,
was bad. It was bad.
right. I mean, I can relate to that very much because um, I'm right now I'm working on this documentary on Salam, and there are some stories that I read about there, which can actually give you this picture that PhD students are expected to know everything about their project. For
Mhm.
example, there is this story that I think that Salam told about his advisor, that his advisor I think said to, probably it was about Salam's advisor or Salam himself, I don't remember, that he actually said that, okay, here's this problem, and you need to read this book by Littlewood. So Littlewood, I'm sure you know
Mhm.
about this mathematician
Yeah.
Littlewood. So there is this book by Littlewood. You read it from cover to cover, and if you can't read it, go back to your country. Like that's very brutal. So
Yeah.
there were some PIs who used to do that, and that actually can give you this picture that, okay, PhD students need to know everything and they need to do everything on their own. So I don't blame the people who actually have this thing in their mind. Um, one thing that I skipped, in the start, earlier when you talked about the background independence of string theory.
Mhm.
This is something that I see in a lot of people who are not fans of string theory, that they have this misconception that string theory is background dependent,
Mhm.
and I don't know why they think that. Probably, they are also influenced by small and people like that. But I think one of the reasons that, okay, this is what I think. It may be wrong, but one of the reasons is that the maths that you use to describe, strings in, arbitrary backgrounds makes it seem like it is background dependent. But I think it's just the maths. It's not a feature of the theory, because we know that there are proofs of background independence of string theory. So why do you think that this misconception is so prevalent in the critics of string theory, that
Yeah,
string
I
theory
think
is background dependent?
I think it's what you said. I think it's what you said. It's exactly that. It's because when people first learn string theory, it's kind of done in a perturbative, fixed background way. and people think that okay, this is string theory. It's not background independent. Whereas the difference is that string theory is not manifestly background independent, whereas loop quantum gravity tries to be manifestly background independent. So I think that's and because that point has been pushed by people in loop quantum gravity, I think people have the misconception that string theory results are also background dependent, which is obviously not true. And this
Right.
it has not been countered so much by string theory people in the media as much as maybe it should have been, because I think string theorists also often say that yeah, we need a manifestly background independent formulation and so on. So yeah, I think it's just that, but it's a misconception and it should be cleared. And also, although loop quantum gravity tries to be background independent, it's not, the dynamics has not been solved, so it's can't be said to be like a fully completed theory in itself.
I see. Okay, so now I want to talk about one of the things because of which you are quite well known on Twitter, and it's your writings on different topics of physics, but in particular. And I don't need to tell you this, that your writings are read by a lot of people, not just in India. I think even in the people in the Western world, people in Europe, I know a lot of people who actually read your stuff. So you just mentioned this thing that it's we were talking about background independence, but I think we can generalize that a lot of things that string theorists should have done in for the popular audience, it's not being done, at least right now. I do remember that in the early 2000s there were a lot of attempts by string theorists like Brian Greene and some other people to popularize string theory, but I think that has faded a lot. So do you think that string theorists need to, well, do two things? One of the things is that they need to popularize string theory. And the second thing, which is actually, I think it's a very pressing issue, is that counter the false news about string theory, because there are a lot of outlets which are just giving false information about string theory. So first of all, what do you think about that? And the second thing is that what should be the medium of that? So do you think that just writing on social media platforms is enough, or should we also do some, you know, uh, video work? Because a lot of people who are actually spreading false news about string theory are actually well-known YouTubers.
Yeah. So this, definitely, I think string theory has developed a PR problem. And to a certain extent, string theory community is to blame, because in the earlier days, there was some hype associated with string theory, and string theorists participated in it, which did not always give an accurate picture of what was expected. And people got the wrong impression that, in 10 years, everything will be solved and we will observe, I don't know, strings in LHC or something. So with that wrong impression that was given, there's an obvious expected backlash that now that those promises have not been delivered on, or they have not been delivered on in the way that people had made those promises, people feel like the whole string theory thing is a scam, and it is understandable. And as I was telling you, I started with loop quantum gravity at a time when Lee's book came out, which kind of started the whole anti-string backlash. And even at that time, reading that book and whatever was around at that time, I felt that maybe string theory is indeed like a cult or a scam or something that's not going to give the right results. It's only when you spend some time learning and comparing the different theories, you get a better idea of what is correct. So right now, as an insider, you and I have a kind of feel that when we see this incorrect communications, we feel that this is very, very different from what is actually going on. This is very different from the real picture. So it's definitely, there's a need to put the real picture out there. I definitely agree. And I also agree that this is not being done. So there's hardly any communication that's been done. I think Joe Conlon's book on why string theory was a very good attempt, but it was just this one book. There has not been many defenses of string theory out there in the writing form. And to answer your other question, it has to be done in all forms. It has to be done in writing, in YouTube, in TikTok, wherever you can go. You have to spread the word, because
I think the people who
yeah,
write who read the printed material, those people are actually decreasing in number. A lot of people just watch videos now. So I think it should be
Absolutely,
done in
for sure.
videos, right?
So absolutely, people should do videos. People should go everywhere, to
Hmm.
to paint the correct picture of what is actually going on. Because as scientists, this is one of our scientists. I think of scientists as kind of agents of the humanity's will to learn new things. Okay, so whatever we don't know, whatever as a human society we don't know, scientists are supposed to learn those things, find out those answers, and then communicate them to the wider humanity, to the wider world. And so we are kind of agents of humanity's search for knowledge. And it is incumbent upon us as a community of scientists to also communicate whatever we learn, not necessarily for every individual scientist to do, obviously, but for those who want to do it, there has to be some incentive to communicate. Now, one problem is for active string theorists is that what are you, because this is such a competitive field, what are you getting out of doing this kind of science communication? So that's something that the community has to kind of think about and figure out a way to make incentivize people who want to also do some kind of communication, who want to put the right picture out there, like
Right.
you are doing. But this is something obviously for you. You have to balance your research along with
Yeah.
all the other
Yeah.
communication
It
rules.
affects my PhD in a big way. I mean, a lot of time goes into this.
I was not doing it till I got tenure, so because
Yeah. I mean,
it's
that's
so
a wise
difficult.
move, I think.
But if there is some incentive, if there is some positions for people who want to do it also, where you can balance both kind of works, that would help. So for sure, the community has to think about its PR problem somehow. Maybe the community does not worry about it too much, but I think it should, because of the reason I just said, that
Hmm.
there's some kind of duty for us also to communicate what is going on, not just for to counter the incorrect information out there, but just as to give people the right picture of what is going on, which is important.
Yeah. I think
So
one of
yeah,
the
so all
incentives
everything.
I think one of the incentives can easily be seen. So I think in my previous podcast, I was talking to Thomas Van Riet, and
Mhm.
he was actually telling me, well, so he actually mentioned this thing that this is not a general trend. It is just a bunch of anecdotes, but anecdotes do count about to something. So he was actually talking about this incident that he had, and he was saying that before 2014, he never had any problems with getting funding for projects that involve holography and things like that. But he was telling me that after 2014, there were some instances where his grant proposals were rejected that actually included projects like holography, and the feedback for those grant proposals included, well, passages that looked like these books by Peter Voigt and Sabine Hosenfelder.
Okay.
So he actually mentioned that because I asked him the question that this widespread criticism of string theory on the internet, does it affect the funding situation of string theory?
Mhm.
And if it starts to affect the funding situation, I think then there is an incentive for string theorists to counter this misinformation, because otherwise their funding will just get decreased even more, right?
Yeah, so 2014, I mean, it's been a decade. So even so, the lesson has not been learned, it seems. And
Right.
yeah, I definitely think if the funding is definitely one thing that people should maybe maybe might make people think a little bit more about providing the right incentives. But in general, also there should be more incentives for science communication. This is
Right. I mean, for
important to do.
example,
So there should be.
if you look at what happened to the superconducting supercollider, I think its
Yeah,
funding was cut because of the negative public perception. And okay, some people actually
yeah.
blame the condensed matter physicists for that. That for example, Phil Anderson,
Mhm.
Phil Anderson was one of the people that gets blamed. So I think that can happen to string theory if the public perception of string theory becomes really bad, then its funding is in danger. There is no
Mhm.
question about that. So
Yeah.
I don't know if the active string theorists are just not aware of that, or they just turn their back to this, very manifest danger that they can face. So what do you think it
Yeah.
is?
I don't know. I'm not so connected with the string community. to able to answer the sociological question that why they are not doing it. But I definitely think that that scientists in general can be not aware of such issues, and they can be caught unawares when such funding goes away, when such thing happen. They tend to be not always aware of the undercurrents that are going on in what people are thinking. Exactly as the case of the super collider that you mentioned. And I remember Michio Kaku kind of became a science communicator at that point, and he had written that he realized that one of the reasons that this was cancelled was the failure of communication on the part of physicists to communicate the excitement to the general public, like why this was an amazing thing. So he said that physicists maybe should have said that this is some portal to some, I don't remember the exact words, this portal to some new dimension. Now, I'm not a big fan of Michio Kaku's current
Yeah,
work,
same,
but the
same.
point he made was valid, that you have to involve the general public in this journey. They are they are funding us, and they are major stakeholders in the science enterprise. So you have to keep them involved, keep them clued in, keep them in the loop as to what you are doing, and only then you can expect them to also
Right.
support science.
I mean, I'm not sure why the funding got cut, but one of the reasons that some physicists talk about is that if you look at the fall of the Berlin Wall, after the fall of Berlin Wall, you can say that, well, communism actually lost there. With the Cold War kind of ended after the fall of Berlin Wall. So the physicists were not that important to American government after that. Therefore, they actually just took the funding away. So this is one of
Right.
the reasons that people say that, okay, because before that the Cold War was there, and American government, well, they might have needed physicists for that, so they were just funding physicists. I think so. This is one of the theories. I don't know how truth it has, but anyway, there is one very interesting line in an essay of Steven Weinberg in his book called Third Thoughts. Because he testified to Senate for this superconducting supercollider, and he said to he said in that essay that there was a senator who said that if your project benefits Stephen Hawking, we can give you all the money. And if you look at that statement, I mean, Stephen Hawking is not as big a scientist as Steven Weinberg. I think Weinberg is a bigger scientist, but I think Hawking had a more public popularity.
Yes.
So I think that actually baffles my mind. I mean, how is that happening? But I think it does make sense to some extent that if you try to market it in a way such that you say that, okay, it will benefit Stephen Hawking, then they would give you all the money. Although, I mean, we as scientists know that it's absurd to market it
Yeah,
in that way, but I think
absolutely
it
makes sense.
works.
Yeah, for the general public, it works on perceptions. No one is going to check like your scientific literature and what you have done, your contributions, and so on. And even for the people who are communicating science right now out there, if they can get the kind of people's trust, if they can win the trust of people, then people tend to support them. They're not going to look into their scientific records. They're not going to look into whether uh, someone like Lee's contributions is bigger than someone like Rankin's contributions or whatever. They're just going to read the book, and if they trust this person, they will believe both of them or not believe both of them. So it's about public perception, and there things like celebrity matter.
Right. Yeah, it does matter. So one thing about science communication that I want to talk about is that, so we see that there are a lot of topics in our field, especially high energy physics, and more particularly in string theory, that are very, very complicated. So if you want to make those topics accessible to public, is there any strategy that you employ, or well, that you have planned to employ but you have not employed it yet, that can make these kind of very, very abstract topics accessible to public? For example, if I want to talk about something like uh, conformal conformal landscape to the public, it's just an example. I mean, there are a lot of, I'm sure you can think of much more abstract topics. So is there a set of strategies that one can use to, communicate these kind of very abstract topics to the general public, or do you think that there is no use of, communicating such abstract topics to the public?
No, I think it really depends on whether you can make it interesting to the public or not. And when it comes to abstract topics, I think it's difficult. But the strategy I generally employ is analogies, and I try to find analogies to that thing with something else. And if it's abstract, then it won't be like some concrete thing. Then it would also has to be like in a certain way abstract and different from the thing that you are comparing it with. So you could find something maybe from the world of, I don't know, literature or something, which has some kind of oblique relation to what you are talking about. So like this is not an abstract thing, but to give a example. So one analogy I always use for ADS safety is something that you may have also heard of, is the can of juice analogy, which is, I also have a can of bottle of juice with me.
Right.
So, I say that you can see this picture, and so in this case, it doesn't work because this is a mixed fruit juice, but usually there's a picture of the fruit that is inside. And I say, you can predict what is inside from the boundary by looking at the picture of the fruit. So if this is like orange juice, there's a picture of orange. So that tells you this is orange juice. And holography
That's a
is
good
a little
analogy.
bit like that. Because, because you can say that, from the outside, I can tell what is inside. And another analogy that I have used for the same thing is like, there are two people who speak different languages, but they know the answer to the same questions. But you have to frame the questions in different languages. Again, this is about bulk boundary duality, where you have to, for the same questions, you ask differently in the bulk language and differently in the boundary language. So you have to translate between bulk and boundary to get your, when you work with ADS CFT correspondence, which is one of the challenges of working with ADS CFT correspondence, is knowing how to translate from bulk physics to boundary physics. So these kind of analogies may not be directly related to what you're talking about, may not have like a mechanical analog of what you're talking about, but you have to be creative and find something that might connect the public to something they know, because the way people understand is by connecting with something they know. So if you can find something, connect with something they know, then it works a lot better. But that something need not be a mechanical analogy, in the sense that you may not find like something in the physical world that has that kind of relation with something you are describing, but it could happen in the world of ideas or the world of relations, the way people relate to other people and so on, that you might be able to find something which you can then again relate to something else. So that's right. The way I work. And it's for me it involves a certain amount of trying to find things, imagining things, and it's one of the challenges of science communication that I really enjoy, to try to come up with these analogies. It can be quite difficult at times, but it's also fun to try to do that.
Right. One thing that's very important feature of science communication is something that I have dealt with a lot, and I've seen you dealing with that particular thing a lot as well, and that's combating pseudoscience, because there are a lot of things which are popular in general public, probably because not probably, but most of the time it's because a very influential person is saying such kind of nonsense. So do you think that, for example, okay, so I think we can divide it into two parts. So one part is that there are people who have no expertise in the things that they're talking about, but they are, popular in public. So whatever they say, for example, I don't know if we should take names. I mean, I won't have any problem with. I don't know if that can be a problem. So, for example, I think you wrote this article about Sadhguru talking about different, very, very, nonsense things. So that's just an example. There are many other things, many other people who are talking such kind of things. So, but he's popular. So, how do you, combat pseudoscience when the person who is spreading pseudoscience is very popular, but not an expert of the field? And the other part, the other case is that when the person is an expert, for example, I think you know about the Roy Kerr article about black holes not having singularities. Now, I think that's a very different case because Roy Kerr is, a very big name in black hole physics. So I think the strategies there may be different. But
Yeah.
let's come
Another
to this
example
first.
would be the Harvard astrophysicist.
Yeah, Avilov.
Yeah.
Right. Right. Yeah. So I think that's a different category. The strategies there may be different, but we will talk about that. But how to combat this area where the people are very influential but not experts of their field?
I haven't done a lot of work in this area, so I don't have a lot of experience, in busting pseudoscience. I had written that one article. That's about it. It's challenging because it's very difficult to convince people what is right. And I have kind of, from my past experience, I've kind of given up on trying to convince people on most things. So my strategy in science communication is mostly like telling people what is right and hoping that by osmosis people catch on to the scientific method that's reflected in the ways of thinking that we present, right? So what we want to communicate to people directly or obliquely is that there's a method to how we do things. It's not something that we don't pronounce things. We don't just give some say something without logic, without proof, without evidence. Everything comes from evidence. Everything comes from logic, and those are the ways that science progresses. That you have to give people, you when you do science, you have to make it evidence based. So when someone is saying something that is not evidence based, we challenge it on those grounds. When I say that this is evidence based, this is not evidence based.
Right.
But unless this uh, and we just discussed this about how the senator said that we will give money if Stephen Hawking is involved. So the cult of celebrity is something that is, and the Sadhguru thing is not so different from it, in the sense that people believe the person who has some kind of authority, and they
Right.
tend to trust people in some kind of authority. So it's very difficult to combat it. In fact, what we can do at best is put the right information out, and through our work we should also try to reflect that why this is the right thing, what is the method that we're following, so that people can themselves apply that scientific method, and they can catch on, and they can figure out that this person is not saying something that is correct.
Right.
Not
But
that I don't.
let me
If
play
you have any
let me
thoughts,
play a
like, yeah,
well,
go ahead.
let me play a devil's advocate here. So, I mean, I'm sure you know about this thing that when such kind of pseudoscientific claims are made, they do have a pinch of truth in them, because they use a truth and then construct a conspiracy theory or a pseudoscientific belief around that. For example, I'm sure you know about this claim that you should not sleep facing north direction because of
Right.
the Earth's magnetic field. I think it will affect the iron in your blood. Now, the thing is that magnetic field does affect iron. That's true,
Yes.
right?
Yes.
So I
Earth
think
does have a
people may take that
magnetic
as evidence. Right?
yeah. And Earth does have a magnetic field.
Yeah, that's true as well, right? So people that may take that as evidence.
Yeah.
Okay, this is the evidence. So
Yeah.
how to convince them that okay, this is not the evidence for what he's saying? I mean,
Yeah.
because
So
this may be
yeah.
taken as evidence.
Yeah. 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 But then you have to, puncture that logic by saying that why this is not enough, why this is not sufficient to affect the iron in our bloods, what is the state of the iron in our bloods, so that it is not affected by magnetic fields and so on. Which is what this is one of the
Right.
things that Guru had said, and this is one of the things I had written about in my article, that
Yeah.
this does not happen because of this reasons. So those are the points where you can say that this is the flaw. And of course, there's always a pinch of truth in any kind of untruth, and then you point to it and you say that these are the reasons why this is not true.
Right. Okay, let's come to the second category. The second category is where people are experts of their fields, but still they are making nonsensical claims. For example, this Roy Kerr article about black holes, and you also mentioned Avi Loeb, who is
Yeah.
he's an astrophysicist, but he makes very nonsensical claims about aliens. And there are
Yes.
some other, examples that I can think of. I don't remember. There was this cosmologist who was talking about some ghosts in cosmology. I don't remember the name of that cosmologist, but he was a well-known name. Yeah, I don't remember exactly who he was. And then there was this So I don't remember the name of that physicist, but I think in last year there was this 900-page proof about the stability of black holes. It was a mathematical proof.
Okay.
And one of my Indian colleagues actually met one of the authors of that paper, and he's an expert of his field. But he
Hmm.
was saying that something like that. It's mathematically impossible for Biden to win in the election because of this. I was like, what the hell are you talking about? So, I mean, these are experts of their fields, but still they're making. So, okay, we can take election out of this thing because election is a different thing. But let's talk about, for example, this Roy Kerr thing.
Hmm.
How does an expert of a field end up talking such nonsense thing about, the same field in which she's an expert? So, do you have any thoughts on that?
Not really. I have not actually read the Royker article. I don't know what the people
Okay.
are thinking about it. Actually, I have not. I'm completely ignorant about this particular thing. In general, yes, it happens that people. So there are two things again, right? When
Mm,
someone is an established physicist, but they're talking nonsense about some other field,
right. I mean, for example,
or
Freeman Dyson was a climate denier.
yeah,
We know
yeah,
that, right?
yeah. But the other examples are like people who are kind of crackpotish, who are also maybe experts in their field, but they're talking nonsense about physics. So like Wolfram, like Weinstein, there are people
Yeah.
who have own theories and so on, and won't be denied, won't stop, won't be stopped. So these people again, it's ultimately all you can do is put the right story out, put the right put out the criticism, and tell the world about where they are going wrong, why this is wrong, why the whatever it's called, Oma Noma or whatever it was, is not an alien artifact. What are the proofs against? What are the reasons to believe that it's not an alien artifact, and so on. But
Mm,
at the end of the day, we know that it's harder to kind of burst fake news than spreading fake news. So it's called some Brandolini's law or something, where you have to put more effort to disprove some nonsensical thing
yeah,
than
of course.
spreading it out in the world. So it's difficult, it's challenging, and when experts do it, you still have to point out that what is true is not the word of the expert. What is true is like following the method. Is it evidence based? So you put out the evidence and you make the argument based on the evidence. That's how
Yeah.
people have been doing it for all the time, and I think the only way to do it is in different media, different forms. Just keep doing it and not cede ground to people who are not cede ground out of respect for their authority, not cede ground out of respect for their money or any other thing. Mhm. Or
Right.
prestige
I
or
mean,
anything. You
I mean,
just
this
keep.
question. I think this question. Well, especially after 2020, I think this question has
Mm.
become really important, at least for me, that how to convince people that who is an expert. Because we saw, okay, I mean, physics experts may not be very, sorry, let me back up. So, I mean, misrecognizing physics experts may not be very deadly for our civilization, but we saw what happened during COVID. I mean, because
Yes.
everybody was being an expert on COVID. And I
Yes.
think because of that outbreak, it becomes very, very important to recognize that who is an expert and who is not an expert. And when experts, okay, medical experts, I mean, they are much more important to be recognized. But if we
Yes.
talk about physics, then misrecognizing physics experts
Mhm.
can be, not deadly, but it can be dangerous as well. But when physics experts actually do such kind of things, where, for example, this Roy Kerr article, I think that makes me afraid that people will just, stop believing on experts at all. I may be very paranoid about that, but I think it's a possibility at least. That's why
Yeah.
I'm very, yeah, please go on.
Yeah. It's definitely a challenge of our times. This is something that the times have posed this challenge to the scientific community, that and to everyone
Yeah,
in general, that whom do we trust? What do we trust? Does everyone have to do their own research? And is it possible for everyone to do that own research? Should we trust experts? What if experts are wrong? What if experts are saying something nonsensical? The question of trust in science and trust in scientists, the eroding trust in science. This is one of the challenges that we are facing right now, and I don't have the answers. I don't know. To my mind, we have to prioritize always the scientific method, and whenever we communicate to the public, we have to make that communication evidence based. We should not be saying that I'm an expert, take my word for it,
Mm.
but I'm saying this for this reason. So it has to be prioritized, but that too can have negative effects, where people might be fooled into believing, people who do not have the requisite knowledge might be fooled into believing that some person who is posing as an expert is a real expert. So it's a difficult kind of challenge, and right now the only possibility that I see is generally increasing the volume of science communication, so that people get better ideas about everything, so that they have a kind of better base of knowledge based on which they can make their decisions. Instead of, when you don't have like any base of knowledge, anyone can seem like an expert. But when everyone is more well informed about everything, then it's more difficult to fool people. It's still possible,
Right.
but it's more difficult. So I think what we can do is we can make it more difficult to fool people in general by making them well rounded and well informed in different topics.
Right. I have another question, but I will come to that a bit later. Uh, but I want to continue on this a bit. So, I mean, it looks very dangerous to me, because if we are unable to tell people who is an expert and who is not an expert, then it will give even more space to people who actually try to spread pseudoscientific ideas, and it also gives space to what we refer to as crackpots. I mean the people who are spreading pseudoscientific ideas are also crackpots, but they are not popular. Sorry, they are also popular, but crackpots are not always popular. I mean, I'm sure you also know about such people who try to solve, who try to disprove all of the physics in one paper. I'm sure you know about them, and they
Yeah,
are
there is.
kind of dangerous. Probably you know about this. Do you know that there is, a crackpot session in the annual meeting of American Physical Society?
I didn't know this. Okay.
So that's actually very interesting, and I learned about that, I think, probably 1 year ago, that in American Physical Society, if you give your membership fee, you
Mhm.
can have this session, and in that session there are crackpots, giving their talks to other crackpots. And they had to do it because there was this incident, I think in the 50s, if I'm not wrong, where there was a person who sent his paper to American Physical Society to be published, and they did not publish it. So what he did is that he took his gun and went to the headquarters of American Physical Society and shot the first person, and it was a girl, and she died. So after that, they actually made sure that, okay, you can give your talks here so that nobody dies. So these crackpots
It
can be
talks
really
everyone.
dangerous. What?
Yeah, so they just allowed everyone in. Like, okay,
Yeah. So these
that,
crackpots can be very dangerous. I mean, uh, if some young person is listening to this conversation, I would say that it may seem that fighting against pseudoscience is a safe job. It can become dangerous. I mean, for example, I don't know if that comes entirely into this particular thing, but we do have incidents like, for example, in India there was this assassination of Narendra Dabolkar, right?
yes.
And even in Pakistan, I mean, in Pakistan there are a lot of such incidents, but I mean, the assassination of Narendra Dabolkar, I think it's something that gives people this, should give people this idea that this is not a safe job always. I mean, it can become dangerous. Um, anyway, so let me come back to the question that I wanted to ask before. So, do you think that if there is a scientist who is doing popular science,
Mhm.
and he or she becomes very famous because of this work, then this fame changes that scientist? Because I've seen some people changing
Yeah,
and
again,
becoming
it varies from person to person. We know
right.
examples of people who have changed, but we also know examples of people who are still kind of very into science, who are kind of still going back to the basics, who are still scientific, who still, you know, don't hype things up. So there are examples both. Everything changes people. Everything that happens, every
Right.
everything changes people a little. So yeah, but it's even if you become famous, it is kind of, I would hope, incumbent on scientists to prioritize science communication, prioritize correct communication over your own celebrity. So I think I made a fun, like a tweet about a joke about this, that there's this duality called dollar duality, where when you become famous, when you get a lot of money, your communication becomes very, very, you know, uh, fantastic
Word?
and
Oh,
not correct.
fantastic. Okay.
Not fantastic in the fantastic sense, but more fantasized and
Oh, okay, I
incorrect.
see.
We have seen that. We have seen that with some very famous science communicators.
Right. Okay, so we actually received quite a few questions from the people that I should ask you. So I'll just go to the people's questions now. You may we can make it a like a lightning round, so you don't have to give very detailed answers to this question. But you can take your time. I mean, it's up to you. I have plenty of time, so however time you want to take, you can take. So there's this question. It comes from Twitter, I think. It says that can anyone become a good physicist, or is there a certain benchmark intelligence? If there is such a minimum benchmark, how high is that? I think we talked a bit about that, but if you want to say anything about this.
It's a difficult question. What do you think?
Well, I mean, I think you don't need to be a genius in order to, become a physicist. I mean, you can be of average intelligence, and I mean, there are a lot of people, I think, whose contributions have gone into the developing the physics that we have today. For example, if you look at experimental physics, all of the people who are working on experimental physics are not geniuses, but their contributions are very worthy of praise. And they are underrated, by the way, obviously, because there are thousands of people who are working on these things. So you cannot appreciate every single person individually. So what I want to say here is that there are a lot of people who are working on physics, but you don't have to be a genius, because every person who is working on physics is not a genius. So this is what I want to say. I mean, the question that this person has asked, I think that person is assuming as if there is, you know, uh, some quantifier of intelligence. I don't think there's some quantifier of intelligence. So I don't know how to address that particular part without having a quantifier. So this is what I can say. If do you want to say anything about that?
Yeah, I think I agree with you. And I think, as you were saying, intelligence is such a kind of you know, multifaceted thing. It's difficult to say that, this like five, you have to have intelligence of five or something, because you could be. I have seen people who are smart in one thing and not quite as smart in another thing. So it's a lot about. You could have average intelligence, but there are a lot of people who average can be like average, or it can be like a sum of different parts which are at different levels. So I've seen people who are very smart and very capable at certain things, maybe not so much at other things. And it's a lot about finding
Right.
your own niche and finding out what works for you, what is the kind of problem that you are good at. So some people are really good at coding and problems related to coding, for example, and some people are good with their hands, like people who go into experiments. So those are also kinds of intelligence. So there are different kinds of intelligence, and it's not about, like, if you want to go into physics, it's not about asking like, am I smart enough? It's about asking like, does this give me enough meaning? Does that bring me enough
Right.
joy to do it? So if you feel that way, then you should do physics. But don't let this kind of questions deter you from doing physics, would be my message.
I think one thing that I think we can mention here is that you should not ask if I'm smart enough. I think you should ask if you're stubborn enough, because many a time you just need to spend a lot of time with problems. It's just about your
Absolutely.
stubbornness. I mean, for example, the
Perseverance is
person
more
who,
important than intelligence.
yeah, exactly. Okay, so there is another question. I don't, I don't know if this is even true, but okay, there is this person who said that, what is your view on Einstein's statement, who has not made, sorry, so this is a statement, who has not made their greatest contribution to science before the age of 30 will never do so. I don't know if Einstein even said that, but
I
even
don't
if he
think.
said that,
Yeah.
yeah, I think it's very hypocritical if he said that, because I think his GR came after when he was 30. So, I mean, It doesn't even apply to Einstein himself. Anyway, but I don't think that's true. Even if Einstein did not say it, I think the statement itself is not true.
Yeah. No, it's certainly true that human intelligence peaks at, like, your abilities and so what happens is when you're younger, your brain works, you're really smart, but then you don't have
Mm.
enough knowledge to work on things. And then slowly, one thing peaks, your abilities. Every ability peaks at a certain age, and then slowly it tends to go down. In sports also, you peak at a certain age, and that peak can happen at different ages for different people. It's not the same for everyone, but eventually there is some kind of decline. But at the same time, you are more knowledgeable as you get older, and you have more wisdom. So even then, you can operate at a very high level. You can make contribution. And we have examples of people like Weinberg who are making like stellar contributions at the age of 80 and beyond.
Mm.
So it's not like that, but obviously on an average there is a trend that there's a certain age range where people peak. Was probably 30 in Einstein's time, really, because at that time the prerequisites needed to make a contribution were less. All the people, Heisenberg and so on, were making stellar like seminal contributions at the age of 20, which is not
Yeah.
so easy now. But
Yeah. They didn't
now,
need to learn quantum mechanics. That's why.
yeah, yeah. So now, maybe that age gets pushed. So
Mm.
I don't know if there is a particular age. If we know it, people say late 30s is usually when people are at their peak, when your cognitive abilities and your knowledge of the field is kind of together optimized. But we have many examples of people like Pauling, another example, people at very senior ages who have contributed. So definitely, if you are
Yeah.
beyond 30 and if you have not made, if you have not won the Nobel Prize or something yet, then I would suggest not giving up. Although
Yeah.
the problem is, if you make a contribution at 30, then you might expect to get Nobel Prize in your lifetime.
Yeah. Exactly. That's what I was gonna say. That I think it's very hard to get a Nobel Prize at the age of 30 now,
Yeah,
because I mean the delay between. I mean, okay, if your work is really groundbreaking,
yeah,
then you may get a Nobel Prize in 1 year or two. For example, the Nobel Prize for gravitational waves was given in just 1 year, but
yeah.
many a times it takes a
The
long time.
theory goes back to like 50 years ago. So Kip Thorne
Yeah, exactly.
did his work in the 60s or something.
Right. Okay, so this question is specifically about India, so I think you should talk about it. I don't know if I can talk about it. I have some, knowledge, but I think obviously you'll have much more knowledge about it than me. So the question is that does he believe that there is a big lack of quality faculty at the level of high schools in India regarding physics, so that the students at that level don't get the feel about the beauty of this subject? I have seen a lot of students trying to dodge physics questions.
Hmm. So the question is like, are school teachers good in
Are good
general?
enough. Yeah.
Yeah, that's a difficult question to answer again. I mean, India is a huge country with diverse
Yeah.
population, and there's a lot of inequality. So obviously, you don't expect the same kind of schooling everywhere.
Hmm.
I don't think it will be, the answer would be too different from India or Pakistan. It would be roughly the same. The level of school teaching is, I would think, similar across the subcontinent.
Right.
There are good teachers and there are bad teachers. Generally, very difficult to give a single answer to this question.
I
Now,
see.
it's true that there are places where there are very good school teachers who inspire students and kind of get students into physics. There are other places where the level of school teaching may not be as much. In general, you have to look at how well school teachers are compensated and things like that. What is the incentive for someone to be a school teacher? Now, it's not it's not a very glamorous job. So obviously, you may not be getting the best people there. Also, because in India there is the IIT JEE, which is a
Hmm.
competitive exam, and where there's a huge ecosystem of coaching classes. A lot of people who might be talented teachers are attracted to there, kind of shifted to there, which makes school teaching again more difficult, because a lot of people who might be good teachers would go and work in the coaching centers. So these are some challenges that are existing. But again, I personally don't have as much knowledge of the school system to be able to give an answer to this question. I only know about my school and such. So in IIT Mandi, we do some interactions. We have some interactions with school teachers. We have some training sessions, programs for school teachers. And through that, I have had some interaction with school teachers from Delhi. And a lot of them are very motivated and want to learn like what we know and pass it on to their teachers. But again, as I said, these are some teachers, and it really varies from place to place, from teacher to teacher. It's difficult to answer. So if you
But
have any,
also,
I don't ask.
I mean, I would say the same thing because I think I am not quite aware. I mean, the question was about India, but even if you talk about, where I come from, Pakistan, I don't think I'm very aware of school teaching in Pakistan because I think I'm more concerned with university teaching. So I don't think that I can give a good answer to that question. But I think there is one question that I can, discuss and the question is that suppose that if teachers were compensated, well, so suppose that compensation was not a problem,
Mhm.
then do you think that PhDs should consider teaching in schools?
Yeah, why not?
I mean, but do you think that you need a PhD to? Because I think there are people who are divided on this. Some people think that yes, PhDs should consider teaching in schools, and their arguments include that. I mean, if your PhD is teaching in schools, it can be a role model for that, for the students, and it will obviously bring quality to the teaching. But some people think that probably it's waste of time for a PhD student, and that person should just do research and teach at the highest levels.
I mean, it really depends on the student. I mean, what they want to do. If this is something that they think
Right.
that teaching at schools is their calling, then they should teach at school, and they might be
Okay.
able to even balance research with it. It's
I
not
see.
impossible if they have the time. So it really
Okay.
depends on the person. Varies from person to person what they want to do.
Right.
I I,
Because
I
I
don't
because I
I don't have an answer that is at the level of you have to do this or you should do this.
Mhm.
Answer is always going to be like, what do you want to do? Is it the
Yeah,
best?
surely we cannot tell anyone what to do. But
Yeah.
my question was that would you advise a PhDs to consider teaching at school? That's the question.
Well, right now, I mean, given the level of compensation, mostly people want to do it because there are other better compensating options for PhD students. So it's very unlikely that someone would want to do it. And if someone wants to teach, teaching at a university or that kind of level might be, you know, again, better compensated.
Okay.
However, if the compensation is not an issue, if someone, and again, it really comes down to whether this is what you want to do, whether this is your calling or not, whether this is something that teaching students, because teaching school students is really different because at that age, they're still forming, their minds are still forming. And that is the age where you can impress them the most, where you can influence them the most. So if that is something that appeals to someone, if that is some, and it is appealing to a lot of people to be able to influence them positively at that age, when they're still forming, they're still kind of finding their ambitions, what they want to do. And a lot of people go into science because they had this one school teacher who was really influential. A lot of stories about
Yes,
this was like that.
exactly.
So if you want to be that teacher, then by all means. But again,
Sure.
if there's something else, yeah.
Okay, so there's another question. I think it's again a very general question. So if you want to make it a bit specific, you can. So the question is that what are the things one should consider before going for a PhD?
Well, my answer would be like, again, the same thing I was saying a little bit earlier, that you have to see, if you are if you are someone who is unsuitable for a PhD, and then you go for a PhD, you will be frustrated when your research doesn't work out. You will be sad when your ideas get scooped or your ideas fail to compute. And if you're suited for PhD, exactly the same things will happen. You will still be frustrated when your calculations don't work out, and you will be
Yeah.
sad when your ideas fail. So it's not different. The different is whether you are someone who wants to come back to research after, when you have those frustrations, when you have those failures, you still want to come back and do it. because you, at some level, you have to find meaning in it. You have to find joy. You have to enjoy the process of learning, deep diving into a subject, going down those rabbit holes, trying to do those computations. If that sitting and doing computations for hours, if that does not is something that you don't enjoy, when no one else is looking, just by yourself doing those things, is something you don't enjoy, then you will struggle. I'm mostly talking about physics PhD, but in general, if you don't enjoy the process of learning, you will not enjoy spending like 5 years doing a PhD. If that does
Right.
not give you like meaning, then it's not for you. Don't I would not suggest someone to come to PhD to prove how smart they are, you know, because then you, even when you do well, you will be miserable and you will make a lot of other people miserable, because there are people who kind of come to PhD from that angle, where it's best to come to PhD because you enjoy the work. You know,
Yeah.
it's not glamorous work. It's not, you won't, make it to the cover of Times, but you will have, if you're suited to it, if you enjoy it, it's a good life.
I mean, it's a sad state of affairs, but the reality is that I've seen a lot of PhDs who should not be, who don't even deserve a master's degree, but they have
Mhm.
PhDs because they have just done PhDs, but they don't know enough about their subject. So I don't even know how they got their PhDs, but there are a lot of PhDs like that. So I think most these people are mostly doing their PhDs because they think that they will get some promotion in their jobs.
Mhm.
I think that's probably the only reason. Not probably, but actually the only reason. Okay. Okay, so this next question is actually making a claim. So before asking that question, I would say that so at least in the field in which I work as an outsider, I see that there are a lot of institutes in India from where a lot of good work is coming out. For example, TIFR is a good place. ICTS, I mean, ICTS is part of TIFR, and then there are some IITs, and then you have HRI. So
Mhm.
but this question says that why are Indian institutes not doing well in research? So first of all, I don't know if that's true, but if you think
Mhm.
it's true, then why do you think that's the case?
Well, as you said, I mean, I don't think, again, in my field, I can't speak of
Mhm.
other fields.
Mhm.
Uh, it's not really true, because at least in high energy physics, theoretical high energy physics, a lot of good work is coming out
Yeah,
regularly, at least given the circumstances. Now, one has to understand the financial constraints and so on. In a country like India, we are not paying salaries like USA or Europe or even China. So, but even with those constraints, I would say in these fields, definitely good work is coming out of research institutions. But again, in general, if I want to answer this question in general as to why science in India is, not at par with US or something, then it comes down again to the question of funding. If you look at wherever science has flourished, whether it's in the USA or in the erstwhile Soviet Union, there was a lot of science funding from the government, which helped science flourish. For USA, after around the time of the Second World War, there was a lot of money put in science. Similarly, in USSR, there was a lot of money put in science in a different way, picking up talented people from the school level and so on, identifying them and so on. But there was a lot of funding. So all problems can be solved by funding. And we we see this in, for example, the case of cricket. Like in the 90s, Indian cricket was very different. But as soon as the money came in, now it's like unrecognizable. So all those problems got solved
yeah,
by money. But of course, whether one has to put so much money in science is something that policymakers have to decide, because they have to balance everything and figure out what is the priority of funding in science. Now, outside
right.
of funding, outside of money, there are other things also which one can do to improve science. So the science is doing science is kind of I would say similar to entrepreneurship in some sense. There are similarities, not exactly the same, but there are similarities in the sense that, for example, in India, it was difficult earlier days to run businesses, because there were a lot of regulations to check corruption. So nowadays we hear about the ease of doing business in India. The government is trying to improve the ease of doing business. Similarly, the ease of doing science also has to be improved so that people don't have to worry too much about the bureaucracy. One story I have recounted on my Twitter was that I was trying to organize some conference, and then I had asked for permission to postpone that conference, and I had made that request a month earlier, and this was to some funding agency who were paying for that conference. So I sent the request to this funding agency, and then I received a response, positive response, that yes, go ahead and do this conference. But the response came a week after my proposed date. So already when I wanted to do the conference was
Yeah,
gone. And after that, I got the permission to do the conference. So unless I had a time machine, I could not do it. So this
I think
kind of,
this is what they were
yeah,
asking you to do, the invent a time machine.
maybe,
Probably.
maybe that was,
Yeah.
it was the thing. But this kind of, if the ease of doing science is increased, that will be good. Another thing is, of course, again, to use the analogy with entrepreneurship, there's a most of us in the subcontinent have the culture of doing what is safe, valuing security about this thing, and this is one of the reasons why entrepreneurship is not great. It's not does not do well because risk takers are few. So then, but you cannot do good science without taking risks. If you do like 9 to 5 science, then the results will be pedestrian. You can't produce like breakthrough results by playing safe in science. So that is another thing. So people have to kind of get that risk taking mentality more. And finally, we know that another reason why entrepreneurship does not function well in India is that there is a lot of inequality, and the in entrepreneurship, if you want to start a business, you have to have the capital, and not everyone has the capital. Similarly, for science, in any country which is lacks equality, that a lot of people are not able to do science simply because they have families to feed, they have to get a job quickly, they're not, they don't have that kind of privilege. So it is needed for there to be scholarships and for there to be resources so that such people also can come and do science. So with those bridges, or to help out people who might be interested in doing science but cannot do it for financial constraints, would be a big help, because that would enlarge the talent pool by so much. So these are some reasons
Right.
I think science can do better. Science can be done better if these things were to change.
Well, obviously, you know much more about me. Sorry, much more than me about the state of entrepreneurship in India. But don't you think that entrepreneurship state in India is better? Because I think uh, there's a good startup culture in India, and with shows like Shark Tank India, people are actually encouraged to do more and more startups. So, do you think that entrepreneurship is getting better and better in India, or do you think that
Getting better and
that's
better
not
in the last decade or so, and
okay?
uh, and there is a support for it, and there is the ease of doing business and so on. There's a support for it. People in power want it to improve, and similar push for science would also help science improve.
I see. Okay, so the next question is that can you give us some of your favorite books? And well,
Books.
this question has two parts. So can you give us some of your favorite books, and what is your favorite equation?
What is my favorite equation? My favorite equation is, this is a cliche answer, but it's Einstein's equation.
Sure.
It's my field equation, not E is equal to MC square, but the field equation, which is absolutely, I think, a beautiful equation. Dirac equation is also up there. Definitely, it's one of the best. Uh, Favorite books. I have no. Is it about favorite science books or just favorite books in?
I think they have not specified it, just favorite books. I mean, I think you can tell any books you want. It's fine.
I'm a big fan of the English writer P.G. Woodhouse. So a lot of P.G. Woodhouse books are my favorite. I
Yeah,
can't answer this off the top of my head because it's I can't, because I'm just sitting before my bookshelf. But in the recent times, I don't get a lot of time to read, so it has not been. I've not been in touch with literature for a while.
mhm.
But P.G. Woodhouse is my favorite writer, and out of science books, I really enjoy Brian Greene's books.
Okay. Any particular book that you want to mention from Brian?
Fabric of Reality is, I think, the first one I read, and
Okay.
it's still probably my favorite. One of the best science
Okay.
books, physics books.
Physics books. Okay. So the next question is that do you think that do you think that we need to establish more IISERs?
Need to establish more. Again, this is a policy question. I cannot answer.
Yeah,
This
but
one.
what do you think about this?
Like, see, the good thing. One of the good things about IISERs was that they had free education. So the people who were studying there were getting like full fellowships, and they were even getting some money. But that has been discontinued now. So one of the things that IISERs were doing was kind of helping people who were not from an affluent background to get into science. So I would think that that would be the priority. Instead of starting more IISERs, if we could get back to that, if we could have people from scholarships for people not from affluent backgrounds, more of them. Now it's less. If we could have more of those scholarships, then it would be a really positive step, and it would help a lot of people to study in IISERs.
Okay. I think the next two questions we have already covered. So they are more about buzzwords about quantum physics like consciousness and magic. I think we did talk about the pseudoscience stuff. And the next question is about, again, I think we did talk about this Sadhguru and quantum mechanics. But there's another name I think that we didn't mention, but there are a lot of names like that. But do you know about Abhijit Chavda?
No, I don't know who this person
No.
is.
Okay. So Abhijit Chavda, I've listened to some of his stuff. I think he's one of the people who is spreading a lot of pseudoscientific stuff. Uh, for example, I think one of the things that he says is that calculus was actually taken from India, and then it went to Newton, and then he actually claimed that he invented calculus. I mean, there are a lot of stuff that he says, but yeah, he's one of the other people. Anyway, so the question was like kindly ask him to expose Abhijit Chavda and Sadhguru. I was like, okay, I mean, exposing someone takes a lot of time, but I think we did talk about them, so I think it's fine. So the next question is, I think we kind of talked about it, but if you want to add something to it, you can add. So the question is that when is India going to catch up to US and China in research numbers? Well, I
Yeah,
think we
talked
someone
about
can add to it. What?
Yeah. Well, again, numbers is not something that one would one should focus on. One should focus on
Exactly. This is what I was going to
quality.
say. Yes.
Yeah. So research numbers is the wrong metric to focus on. Although a lot of things are focused on that right now, but in my mind, it doesn't matter what the numbers are. You have to focus on improving quality. That's what will last longer. That is what will give you mileage. The numbers are just the completely wrong way to judge research. I mean, it's okay if someone is not doing any research, you can say, okay, well, numbers are like a way to judge a metric then. But if you really want to judge research, it cannot be done by numbers. You have to let scientists give them a free hand and let them improve the research quality instead of holding them hostage to some number, some metric.
Yeah, because I think H index has become a very dominated metric. It
Yeah.
should not have become a very dominated one, but I think it has become. And there are a lot of universities where promotions are decided on the basis of H index, which should not be the case. I think that's very sad.
Yeah,
Uh,
very sad.
and there, what?
Yeah, that's very sad.
That's very sad. I mean, because I know, okay, so I don't know about India, but I think in Pakistan we had a lot of people who actually made a cartel. We call them citations cartel.
Okay.
And what they do is that they just cite each other so that their H and X can go up and up and up. And this is how they decide their promotions. And because if your focus is to increase H index, then
Yeah,
you can do it without doing quality research, right?
for
Um,
sure. I mean, you could increase H index by self citation. You could keep citing
yeah,
all your
exactly,
papers and increase your H index that way.
exactly.
Makes no sense.
Uh, but even if that is solved, for example, I think there is this. Well, it's a very obscure index. There's this index called P index, and the P
Okay.
index actually takes care of this thing that if there is one author who is citing some other author again and again, they will not count it. So it's
Okay.
more like unique authors. But even that is
Mm.
not the metric that you should be using. It's still a metric because people will actually. find some way to game that metric, right?
Yes.
So yeah, so I think that was the last question from people's questions. So I think I will like to thank you to give us your time for this podcast.
Thanks.
I
A lot of fun.
enjoyed talking to you a lot.
Same here. Okay. See you.
Okay, thank you. See you then. Bye.